Yeah, there's no point. You just ignore the background, right?
Unless you're the end or you know.
Well, we'll see. I'll probably screw up at first because.
You haven't used it here.
No, the last time was in Gila, still in.
I remember
Right.
there's auditorium,
So that was steeply
right?
pitched.
Yeah,
So
yeah.
there's some problem if you write too low, huh? Yeah.
All right, so we are continuing. It's a great pleasure to have Lhc Dixon here. He's one of the most responsible lecturers for years at TASIS.
You mean I write up my lecture notes? Is that what you meant?
One of you that does it on time. In any case, it's a great pleasure to have him here, and he'll give us also 5 lectures on amplitude.
Thanks a lot, Miriam. Yeah, I've lectured here a few times. So I went through my wardrobe before I came out here, and I found 4 TASI t-shirts, although I have 5 lectures, so we'll have to see what I do on the 5th day. But here we are in 2013, and we'll be going back in time on the t-shirts as we go forward in time in the lectures. So I understand that this topic is probably not in the main line for most of you, so you can think of it as a little bit cultural. For example, you can put all the differential geometry that you were learning about, tuck it away in a corner of your mind, bring it out again for Timo's second lecture, because we're going to be doing everything in flat space-time, in Minkowski space, and we're going to be studying scattering amplitudes, and so we're basically going to be interested in what happens when you bring in plane wave external states and then have a lot of plane waves coming back out again. And I'm not going to draw these plane waves after a while, but anyway, so these are the basic objects of interest. Sometimes we're interested in them at tree level. Sometimes we're interested in them at loop level, in which case we'll put little blobs, holes into the blobs and stuff. And so then, of course, we can ask analogously to Timo's question, why amplitudeology, which is just a word I made up for the title of these lectures, to sort of indicate that there's kind of a new field out there which has connections on the practical side and also on the formal side. So one reason is that there's a good practical reason, which I'll sort of start off these lectures with, which is for we could say QCD at LHC. Although it's not all entirely QCD, there's a lot of electroweak physics in there and so on. But it's the need to have a better theoretical understanding of the physics that goes on at the LHC, especially the physics of the standard model, because the standard model is a background to everything you search for at the LHC. It's a powerful machine, but it's not a very clean machine, and you have to know how to handle many different types of background. And just to sort of illustrate some of the where the state of the art is, let me draw 2 Feynman diagrams, which are representatives of what is known and what is unknown. So one thing that's known that was computed recently is the production of a W pair of vector bosons, for example, W plus and W minus. And oftentimes you would decay these to leptons, for example. So this is something that theorists computed over the past few years, and these are gluons. So these, amplitudes make possible the corrections to this process because it's at 2 loops. We'll go into more detail about that. We call this the next to leading order QCD for this process. But if you just go and make the process a little bit more complicated simply by, we'll just keep W plus and W minus here, and add one more gluon, we don't know what these amplitudes are. And so, and these are going to be coming, these quarks are coming out of the 2 protons that are colliding. And so what we say is that we have a pretty good understanding of 2 goes to 2 processes. In this case, the 2 processes are 2 W's. But once we get to 2 goes to 3, we don't know how to calculate these at next to leading order. And so that's one of the practical ideas is practical spin-offs would be to learn how to the structure of these amplitudes better so that we can provide more input to LHC. And I forgot to say at the beginning, you guys should be asking me questions, because if I just sit here lecturing at you, it's going to get boring for both of us. So if you don't ask me questions, I'm going to ask you questions. So it's your choice, really. Anyway, so that's the practical side and of things, is to understand how to do calculations better at the LHC. Just to extend this a little more, NLO QCD is pretty well under control by now. We can calculate processes that have not only 3 or 4, 5, and in some cases 5 or 6 objects in the final state. The LHC can measure more than that. They can measure things with many, many jets out to 8 or 10. We can't calculate all the way there, but for a lot of important processes, we can do that now. And so the sort of frontier is really trying to go to N and LO for processes like this, and in some rare cases, try to go to N cubed LO. There's only one process we really know at N cubed LO, and that's Higgs production. Yep, sure.
Those are perturbative QCD calculations, but you know that all these things
Right. So
there is a balance. You can calculate that in better precision.
yeah. So you have to know what are the uncertainties in the structure of the proton and how big they are. But they tend to be around a few percent. And sometimes you can take ratios of different processes that have similar input in order to reduce some of those uncertainties. But the reason why this thing was calculated at such high orders is because the corrections were very large. And even at n squared LO, you might have had an 8 or 10% uncertainty. And so going to n cubed LO brings it down quite a bit, and it was very useful. There are other processes where, and it also depends on what accuracy the experimentalists can get to. And of course, the Higgs is a very important measurement. It will take them a little while to get to those kinds of statistics, but they'll get there eventually. I will, in response to that, I'll try to say something about that, so this Higgs production, why is that one of the worst processes in terms of how long it takes the perturbation series to converge? I can say a few words about that. Okay, so that, I'll come back to this later, but we're still in sort of the motivation section. So another one is to understand the structure, the beauty if you want, or to gain some formal insights and try to make sense of observations, which is things like why are at least some amplitudes so simple? much simpler than the Feynman diagrams seemingly that go into them. And another is, how should we think of them of being assembled? Feynman diagrams, while they can be used, don't seem to be the best way to understand their structure. And then there are many examples of relations or properties of amplitudes that are invisible at the Lagrangian level. And then amplitudes in different theories can be related to each other in mysterious ways. And one of the examples goes under the heading of gravity is the square of Yang-Mills theory. So we can construct scattering amplitudes for gravitons from scattering amplitudes for gluons very efficiently. And trying to understand that better is very useful. And then we also might want to formulate scattering in a totally different way. And for example, we could throw away, ask if scattering amplitudes can be constructed in a way that has nothing to do with the usual principles of quantum field theory, like locality and causality, but instead have more geometric principles in the right space. And this is the idea behind the Amplitudeology, which I'm not going to cover directly, but we try to give some of the ideas that lead in that direction. And then we also have the ability in this direction to go very deep into perturbation theory in special theories. For example, in n=8 supergravity, we can calculate enough scattering amplitudes at 4 to going on 5 loops in order to say things about its ultraviolet properties. Or in planar n=4 super Yang-Mills, we can do 5 going on 6 loops, sort of at that stage. Then there's also intriguing connections to mathematics. In terms of the functions that describe scattering amplitudes. For example, there are generalized polylogs, which underlie a lot of these kinds of calculations recently at the multi-loop level. But eventually, there are going to be more use of elliptic functions, elliptic polylogarithms, and so on. And associated with this, these generalized polylogs are multiple zeta values, which have a lot of interesting number theoretic aspects to them. And there are even connections to things in the math literature that I can only write the names down. Don't ask me what they mean. Things called mixed Tate motives and other aspects. So there's this mathematical connection too. There's also the hope to extend these techniques to other avenues or other arenas. For example, maybe, still maybe, you could apply to the physics for LIGO in the sense that you, at least for, maybe not for the large black holes that LIGO has already seen, but for smaller ones, the in-spiral waveforms have a lot more wiggles in the LIGO bandpass before the final chirp and ring down. And this range can be done within a expansion in G Newton and the velocity, and you can calculate these with sets of diagrams with certain types of gravitons being exchanged. And the question is whether you could use relations between gravity and Yang-Mills theory to perform these calculations more efficiently. Yep?
So in general, when we have perturbation theories, they're not convergent, they're asymptotic. So why can we go up to 5 and 6 loops without having to worry about this?
Good question. So actually that's one of the things we're trying to explore in the planar n equals 4 super Yang-Mills context. The issue of when a perturbation expansion converges or not, most quantum field theories, the perturbative expansion is asymptotic. You can still learn a great deal from the asymptotic series. It's just that there's a limit on the error you can get to. So let's start with QCD. The strong coupling at the scales at which we're interested in for QCD at the LHC is roughly 1/10. So typically what you find is that that limits your error and says you shouldn't work past about 1/10 or 10 loops. So we're not there yet. So it's not an issue. I mean, eventually it's an issue, and if you are interested in QCD at lower scales, which people often are, then it becomes an issue you have to confront more quickly, and you have to try to resum the series. And there's certain techniques called renormalons, and there are also you need to introduce non-perturbative information from different matrix elements. A little different from the non-perturbative information that Miriam was talking about. And that comes in, you try to extract the strong coupling constant from the decay of the tau lepton, because the tau lepton has a mass of 1.7 GeV. And the scales there are below a GeV, and that's where the strong coupling is much larger, heading towards 1. But it's not an issue for QCD. And then this theory here, planar n equals 4, actually has a finite radius of convergence, in contrast to generic theories. So in generic theories, the theory is asymptotic for one of two reasons usually. One is called renormalons. So those are associated with the beta function in the theory. And roughly speaking, you can have chains of bubbles that represent the coefficient of the first coefficient of the beta function that give you factorial growth in the series. But this theory, as you must presumably know, is conformal. The beta function vanishes, so you don't have any of those. And then a second source for asymptotic divergences can be from instantons. They can give you, they can be associated with factorial growth on the perturbative side. But in the planar limit, which is the limit that NC goes to infinity, the instantons are suppressed exponentially in NC. So we have a chance for it to be a finite radius. And in this theory, we also have a strong linkage to integrability finite coupling techniques that actually show us, for the observables they apply to, that there is a finite radius. Depends on the observable, but for the ones in scattering amplitudes, seems to be closely related to a particular calculation, the cusp anomalous dimension, where we know what the radius is. But we try to check these things by taking these higher loop calculations and taking ratios of successive terms, because that's how you test for the radius of convergence. So that's a great question. Another one? There's a little bit. There is not as much as maybe there should be. So this example of the cusp anomalous dimension is a case where you can sort of study how resurgence happens because you have an exact formula. And resurgence is often about, improving these exponentially suppressed terms. And they're suppressed at weak coupling, but they're there at strong coupling. So there was a paper by a guy named Hatsuda, who, I think that's it, and he was studying the strong coupling expansion of the cusp anomalous dimension, building off some work by Boson and Korchemsky. So you can look for that to follow up. Was there another hand over there? Yeah. Yeah. Oh, yeah. What does it mean to do scattering at higher loops in a CFT? Well, the fact is that there are infrared divergences in all of these scattering amplitudes, and they would all be infinite in 4 dimensions. But that would also be true in QCD. So in QCD, we have this long tradition of using dimensional regularization to fix that. So the divergences, perturbative divergences, can be regulated, and there are poles in the dimensional regulator. And we'll go into that in a little more detail later. But the answer is that you can define the regulated amplitudes at any order in perturbation theory. There's a huge number of poles. There's a finite thing that's left over. And so you can study what are the properties of that finite remainder. For example, you could also take ratios of amplitudes with different helicities where the divergence structure is exactly the same. So then when you take the ratio, that ratio is finite. So you can study those things. Now you can ask, what are you going to use that for in the end? And well, it's planar n equals 4. We don't have any colliders that do that. But you can imagine a world in which planar n equals 4 is the UV regime, and you break it down by generating masses for some of the matter, and then it will evolve into the infrared into a confining theory. And the people in that theory can collide hadrons in that theory. And then the UV structure of the scattering would involve these amplitudes in the same way that we scatter hadrons at the LHC, but the UV structure is in the perturbative region described by quarks and gluons, and not whatever the hadrons are. Also, you can, in the case of the planar theory, these amplitudes are actually dual to other observables. They're Wilson loop expectation values. So if you don't like the notion of scattering in a conformal theory, you can say you're calculating Wilson loops. The Wilson loops are also divergent, and they have to be renormalized. And that kind of renormalization is actually completely dual the kinds of things you have to do in the infrared side in the scattering. Any more questions? This is great. Haven't had to ask you guys one yet. So, yeah. So those are some of the motivations. And I just want to give you a little outline of what I might cover, but it depends on how things go, so we'll see. One is to give an overview, this is very rough, of QCD at LHC. And then as time permits in this lecture, so this is and then we'll describe some of the basics of color and kinematics, the language that people use in this field. And then next time we'll talk about on-shell recursion relations, or BCFW recursion, and as time permits, extra relations between amplitudes that go under the name of color kinematics duality. And that's closely related to double copy, which is a method for implementing this slogan, gravity equals Yang-Mills squared. And then around lecture 3, we'll talk about unitarity, which is sewing trees into loops. And some simple examples of loop integrals. And then we'll talk more about the functions that you encounter at loop level, like these generalized polylogs, the notion of symbols of iterated integrals, stuff like that. And in lecture 5, I'll tell you something about what I've been working on recently, which is a kind of a bootstrap, which we can do in planar n equals 4 super Yang-Mills. So that's the rough outline for the rest of the course. I also have a bunch of references, but I think I'll just put them up on the web rather than go through them here. And I'll also maybe put up a list of references to things I won't have time to cover, but maybe I'll just mention them in words right now. There's been a lot of development in an area called scattering equations, in which you represent field theory amplitudes in a way that looks very much like string theory. So you have kind of something that looks like the world sheet, except that there are equations that instead of integrating over different world sheet configurations, you get pinned to discrete locations, the solutions of some scattering equations. But I just don't have time to cover everything. But I'll put up some references for people who want to go in other directions too, in case anybody does. There's also been soft limits of amplitudes and their connections to asymptotic symmetries like BMS relations in general relativity. There's a whole development about twistor string formalisms, starting with a paper by Ed Witten in 2003 and a lot of work by Lionel Mason and David Skinner and many of their collaborators. There's also a lot of work on the mathematical properties of superstring amplitudes. I'm just going to talk about the mathematical properties of field theory amplitudes, but there's a certain amount of commonality between those two things. And then there's a huge literature on integrability in planar n equals 4 super Yang-Mills work by, there's a big review by Nicholas Byserd and company, and a lot of that's about anomalous dimensions, but there's a lot of connections back to amplitudes, which I won't have time to cover, as well as the formulations of scattering in terms of Grassmannians and then leading to the amplitude-hedron. And also the LIGO applications I won't say much about. But I'll put a list of references for future reading in those directions later, up on the web later. So now I wanted to turn to give an overview of QCD at the Large Hadron Collider. I guess you had, so let's see, erase this. You had one lecture by Tom Lecomte about this, about the LHC on the experimental side. And you're going to get, I think, 4 lectures by Liantao Wang, so I don't want to steal his thunder. So the main thing I want to tell you about is sort of how do you get precision at the QCD in QCD to give good descriptions of the LHC processes, but it's going to be just an overview. But just a few words about what the LHC environment looks like. The collisions are, it's pretty amazing what the detectors can do, because every 25 nanoseconds, or 40 million times a second, there's a collision of 2 bunches, each containing about 10 to the 11th protons. So one's moving this way, one's moving this way. And each of these protons has an energy of 6.5 teravolts, 6.5 trillion electron volts per particle. So if you multiply those numbers together, you get macroscopic amounts of energy. You get on the order of 300 megajoules stored in the beams. And that's enough to melt, that energy will melt 1 ton of copper. So the bottom line is you have to be very careful where you put this beam. There is only one place that whole beam can go and without damaging the machine, and that's down this long abort system. And they have these superconducting magnets operating within a few degrees of absolute zero, which are like this far from the beam. It's just incredible that they can build these things. And the rough size of these beams are about 15 microns this way, and maybe 30 centimeters long. And these beams are so intense, never mind this total amount of energy, but every time 2 of these bunches cross, you don't just get maybe 1 collision, you get 15 to 40 pp collisions every beam crossing. Now, all of these collisions are boring, except maybe sometime one of them is kind of interesting. But they're still there. They're polluting your detector. You will see tracks coming out which roughly look like this. You know, you'll see 30 of these laid out along the beam line. But thanks to their microvertexing, they can measure these things to micron size, and the average spacing here is quite a bit bigger. So for the cases where you have tracks coming out, you can discard the tracks from these events. You know they're coming from some other event. Okay, it's not always as clear as that which one is the interesting event, but quite often it is. That when you have the events that are much more energetic, they also have these tracks. But then you also have all sorts of neutrals coming out here. And these neutrals, they hit parts of the detector that can't very well resolve these guys. So they have a serious problem in in trying to remove the effects for the neutral particles of all these extra collisions. Anyway, it's totally amazing. It works. And they have a certain amount of collision rate. So we call this the integrated luminosity. And for the LHC machine people to compute it, they need to know how big the beams are, how many they had in there, for how long, and so on. But all we need to know is what's the meaning of this number. Well, what are the numbers and what's the meaning of them? So they're always measured in the inverse of a square area. So let me write the numbers down, then I'll explain what they mean. So they collected roughly, well, it depends on what the machine produced and what the detectors recorded. But Atlas, for example, got 35 inverse femtobarns in 2016. And the run has just started this year, a few months ago. And so far, they have 3 inverse femtobarns. And their goal is to get to 45 for this year. So that would represent a little above doubling the luminosity. There were also smaller amounts in earlier years, but this is the main chunk at the current energy. So the current energy is found by taking the energy of the particle coming from the left and the one from the right in the center of mass, which is the same frame as the LHC detectors. And that sum is, the square of it is called S because it's Lorentz invariance. So the square root of S is twice EP, and currently it's about 13, it's at exactly 13 TeV. A little below design, but it's good enough. So, okay, what are these inverse femtobarns? What do they mean? And the bottom line is that for any given process, the number of events that you get for some process I is just found by taking this integrated luminosity and multiplying it by the cross-section for that process. So if you have a process which has a cross-section of 1 femtobarn, you get 35 events. Whether you can see all of those events is another question. And I should also write down that a barn is 10 to the minus 24 square centimeters. But that's way too big. So a femtobarn is 10 to the minus 15 of that. So these are thought of as sizes are extremely small. So let's give some examples. First, let me draw a little picture of how theorists think of the collisions between any two of those protons in the bunch. The picture a proton coming in, we draw it like this to remind ourselves that it's very Lorentz contracted. If we had a side view or a head-on view of the proton coming at us, we might imagine that it's sprinkled with little things called partons generically, but that's just the name for different kinds of quarks and gluons. And of course, the cartoon view of the proton is just the valence quarks, which are up, up, and down. But that's not real life. In real life, there are a huge number of C partons and gluons inside the proton that really do much of the work in a generic LHC collision. And so the way we draw it is that in a collision that has a large amount of transverse momentum by the Heisenberg uncertainty principle. If we have a large transverse momentum, that corresponds to a very small resolving power in the transverse direction. And in that case, we don't have to scatter the protons as a whole. We just scatter off of individual partons. So we pick one parton out of one proton, which might be a quark, and then we scatter it with something coming off of the other proton, or it can be an annihilation process. So the other proton's coming in this way and has a bunch of stuff going off that way. And in this case, I've chosen to pick a quark from the proton and an antiquark from the other proton, and they can annihilate to make either a virtual photon or, for example, a Z boson. And then that Z boson might decay in a way that is relatively easy to see, which is to electron-positron. So we'll come back to the formulas underlying this picture later, but based on that formula and corrections to it, you can calculate for root S equals 13 TeV that this probability is about 50 nanobarns. Now, a nanobarn is 1,000,000 times bigger than a femtobarn. So that says if we plug in these numbers of roughly 40 inverse femtobarns so far, the LHC in 2016 to 2017 made about 2 billion Z bosons. That's a lot. Now, it didn't see all of those. Sometimes these Z bosons decayed to quarks. When they decay to quarks, they get a couple jets coming out. And although that seems like a lot, the number of jets is like thousands of times bigger. And you can essentially impossible to see the Z when it goes to jets. Not always, but most of the time. So the fraction of these 2 billion Z's that were observable was sort of what's the probability of the Z to decay to E plus E minus, or the other mode that's relatively easy to see. Each of these probabilities, it's a standard QFT calculation, is about 3%. So you have to, just to put it in context, you got to multiply this by 6%. So what's that, 100 million? Maybe, roughly. So that's still a huge sample. And they can do some pretty amazing work with that in precision tests of Z production, also trying to measure electroweak quantities with it. They have even more W's, and they're trying to measure the W mass to high precision for doing electroweak fits. Of course, the Z is old news. It was discovered in 1980-something through almost the same kind of process. But we can just run the numbers for one other particle. Might as well do the Higgs boson, since it was discovered much more recently. So we have a similar picture for the Higgs boson, except, as you can see from this, the dominant way of producing the Higgs boson is two gluons coming together. The Higgs boson couples to mass. The gluons are massless. So the gluons can't talk directly to the Higgs boson. So they do it through the heaviest particle we know of, the top quark. Because the top quark couples to gluons. It's colored. It's part of QCD. And because it's so heavy, it has a large Yukawa coupling to the Higgs. So we can embed this graph into a picture like this, put the Higgs here, and then we have to ask, what does the Higgs decay to? For example, maybe it will decay to 2 photons. So what's the cross-section after doing all these N3LO calculations? At the end of the day, actually this is not the total cross-section. This is some fiducial cross-section in the region that the detectors can see it at 13 TeV. You get 63 picobarns. So that's 6 times 10 to the 4th femtobarns. So the number of Higgs bosons in this roughly 40 inverse femtobarn amount of data, multiplying these numbers together, we get about 2 million Higgs bosons. However, the Higgs is much more unfriendly than even the Z boson. The Z boson, at least 6% of the time, it produces a very clean signal that you pretty much know that's a Z. The Higgs is not so nice. When it goes to gamma-gamma, it doesn't couple directly to gamma-gamma either. So this was a top quark. This is dominated by tops and W's. When it goes to gamma-gamma, the branching fraction, which is what I meant when I wrote down these probabilities, is 0.2%. So that means that the number of Higgses that go to gamma-gamma in this sample is like 4,000. And you can't capture all of them. Sometimes they don't come out in the right part of the detector or don't pass certain cuts that you have to put on it. So maybe there are 1,000 gamma-gammas. And what you do with those gamma-gammas is you make a mass of the gamma-gamma, invariant mass of the 2 gamma-gamma 4 vectors, and you get some little thing there at 125, because there's just backgrounds from things like UU bar goes to gamma-gamma that is about, maybe 20 times bigger. So you get this tiny little wart on top of this continuum spectrum from QCD. And this is the best case example because, well, not quite, second best case. Because you observe everything in the decay, you can make an invariant mass bump. In other cases, the Higgs might go to W plus W minus, and you would see what we were talking about in that process over there. You could have E plus mu E, mu minus nu mu bar, and you lost 2 neutrinos. So you cannot make a WW invariant mass bump because you missed 2 of the 4 particles. So you only see these things, and you have background processes from continuum WW. So it's a real challenge. And so that's where you need to know the background better, is in this case. In this case, the experimentalists do not really need the theorists to calculate the background for them. They can draw a smooth curve. Well, they can draw a smooth curve a lot better than that. And then they can look at an excess above that curve. So the theory for the background wasn't so important. But in other channels, it becomes much more important. You have to know what the multidimensional nature of these distributions are in order to try to distinguish the Higgs distributions from the background distributions. And the one case that's even cleaner than gamma-gamma is the ZZ case. So this can go to 4 charged leptons, for example, E plus E minus, mu plus mu minus. And there's very little background for this, but the branching ratio is, like 10 to the minus 4. So I was looking at an Atlas paper that used 15 inverse femtobarns out of that 35 there, and they got 40 events. So one of the reasons the LHC still has a couple decades in front of it is to improve these samples and see if we can test the structure of the Higgs, and of course search for new physics. So, all right. So the question is, how do we compute LHC cross sections for the Higgs, for the Z, for generic kinds of background events? So that's the next thing I want to turn to now. Yeah.
Very little background, right?
This has very little background. Yeah. So the background is basically, one event for this. It's quite clean. Whereas in the gamma-gamma case, the background was 20 times bigger. Okay, so the fundamental formula is the QCD improved parton model. Or it comes from this picture, and it says that if I want to calculate the production of some identified final state, I'm calling it Z just because I'm going to illustrate it by a Z boson. But it is generic. This is supposed to be generic, but there are certain requirements on it, which we can talk about later maybe. So it has to be a suitable final state. If it's not suitable, we can't calculate it perturbatively. And we can talk about that a bit later. And this plus x, this x means anything. And so we call the things that we tend to compute at Hadron Colliders inclusive cross-sections. So we asked for something like a Z boson, maybe with a particular region of the detector. But then we allow for other things as well. And you'll see why we have to do that shortly. And let me just say that we have the center mass energy squared, S, that the machine's operating at. So we have a sum over A and B and an integral over x1 and x2. And then we have so let's draw the same picture as before, but let's just, so that we have everything sort of time ordered, let's move that upper proton over to the left. So this proton comes in here, and this blob is going to represent the, these two blobs are going to represent these functions f, which we'll talk about in a second. And then this blob represents sigma hat. So this coming in here is parton A, and this is parton B. So we're going to sum over these partons. And the picture is that the proton has a certain amount of transverse momentum here, but it's relatively small on the scale of the collision. It's a bound state, and when we boost it to very high energies, we don't change anything that's happening in the transverse direction, and the typical bound state momenta are a couple hundred MeV at the most. So compared to 100 GeV, that's insignificant. So we think of it as a collimated beam of partons, and when we have these hard cross sections, we sort of sample one at a time, but we need a probability for those given partons to have a momentum fraction. So this is we could use P as the momentum of P1 and P2, and the momentum of PA will be a fraction x1 of that first parton, and this incoming momentum will be a fraction x2 of the second proton. So S is P1 plus P2 squared, which is approximately 2P1 dot P2, because P1 squared equals P2 squared equals mass the proton squared is approximately 0 on the scale of these things. But now we want to compute something which is the partonic center of mass energy. And that's S hat, and that's x1 P1 plus x2 P2 squared. And again, the squared, only thing that matters is the cross term, and it has an extra factor of x1 and x2. So that's why when we compute this thing over here, which is the scattering of the partons, so this is called the partonic cross-section, or sometimes called the short distance cross-section. So we divide up the problem into different parts. There are some people theorists working in conjunction with experimentalists, who work out, fit the data, experimental data, to determine these things. So these are non-perturbative, well, I should give them the name first, parton distribution functions. Often just called PDFs for short. Nothing to do with Adobe, though. And so these things are known, in the case of quarks, to maybe almost percent level accuracy. And gluons aren't known quite as well. And I'll just draw them for you, because it gives you a little bit of a feeling at some point for what matters in the proton. Sorry, yeah, good point. I forgot to explain μF, and I should have also put in here, I ran out of room, but this has two more arguments, μF and also μR. Okay, so μF is a scale at which the parton distributions are measured. They're going to evolve with μF through something called the Altarelli-Parisi equation, or the DGLAP equation. If you guys, we'll come back to that later. Anyway, roughly speaking, what it says is that there's an arbitrariness in how we draw, and here's this Z and other stuff coming out of here. So this is, so roughly speaking, μF is the size of this box. Actually 1 over μF, since I'm drawing in position space, and μF is a energy or momentum type scale. So as we change the size of the box here, we change the way we divide up the structure of the proton versus the short distance cross-section. And the reason they're related is because of collinear divergences. As if we're doing the case of the Z where this is a quark coming in, this quark can radiate a gluon. And that gluon, we'll come back to this later, sorry for the poor picture, but the gluon can be very close in direction to the quark. And because of that divergence, you have to, the answer depends on how much of the gluons you include as part of the short distance cross-section and how much you think of as being part of the proton structure. As you change mu f, you move these gluons, some of the gluons from one point to another. The other scale, mu r, which isn't really, well, it's sort of implicitly present in here a little bit, is because the expansion of the short distance cross-section is going to depend on alpha s, the strong coupling constant. And it's really depends on a scale, the renormalization point. And it changes as you change the scale. And so this also depends on mu r, both explicitly and implicitly through alpha s. And if you calculate to high enough orders, these dependencies on mu f and mu r become smaller. And that's sort of how people estimate uncertainties in this game. So, okay, so there's sigma hat for some process. And then we need to make the connection with amplitudes. So So at LO in QCD, this sigma hat is basically a square of the tree level or Born level cross section. Now, I might write a bar over it because in general, this m squared bar refers to the sort of textbook result that when you have two incoming particles with number of initial spin states ns1 and in QCD, we also have to average over the initial colors. And then we have a sum over all the initial and final spins and initial and final colors of the actual matrix elements, which depend on all of these. So you have to compute the matrix elements for each choice of spin and color, or you have some formulas that allow you to do the general color sums or spin sums in a particular way. And you have to compute that unpolarized amplitude, unless you have something polarized you can measure. And then you have to convert the final state sum as just a sum, but the initial one has to be averaged, not only over the initial spin states, which you're probably used to, but in QCD, you also have to average over the number of initial colors. So, for example, in QQ bar goes to Z, you would have a 1/2 squared, 1/3 squared, because the quarks are spin a half, and so they have two spin states, and they have three colors. Okay, so at leading order, we just square the leading order graphs. And let's just illustrate that for. So now we don't draw the protons anymore, but we just have some quarks coming in, and we have to do it separately for the U and D case, and they have slightly different couplings to the Z. And then we square this thing. And in the general case, this process might also have powers of the strong coupling in it. In this case, it doesn't. This is just a electroweak coupling here. So then when we go to NLO QCD, what do we have to add? So we have two types of NLO contributions. And the first type is one loop virtual. So remember that, or the matrix element, we're going to expand it in perturbation theory. And there's a leading term M0, which might have some electroweak couplings in it. But then the next term will have two extra powers of the strong coupling, which we can write as GS squared over typically a 4 pi squared from the loop integral, or alpha S over 4 pi. And there's the one loop term. So what we want is the second order term in M squared. So it has the Born term M0 squared, which we took into account up here. And then it has alpha S over 2 pi times the real part of M0 dagger M1. So when we take the complex square, we get two cross terms, but it's really the real part of the dagger of this with this. So we want to just draw a little picture of that. So to discuss the dagger, the complex conjugate of an amplitude, I'm just going to draw it time reverse this way. And then this sign here means that it's going to be interfered with or multiplied and summed over spins and stuff here. So this is representing M0 dagger, and this is representing M1 for the case of Z production. And really, I should connect this to this too, but and sum over things there. So this is one sample Feynman diagram, although there aren't very many in this case, of the one loop correction to the Q bar, Q goes to Z amplitude. But in general, you take the tree graphs and add loops in all possible ways, and sometimes you can get hundreds of thousands of diagrams if your process is a much more complicated one than this. So that's the first type of correction, the one loop virtual. And then the real correction comes into play. Notice that there are two powers of the coupling from here, the two powers of the strong coupling. In the real corrections, so we can either get gluon emission, so a sample Feynman diagram for that is we have a gluon coming off here, and we have the Z here, and we take this amplitude and add another amplitude, this diagram, add another diagram where the gluon is radiated over on this side, and then square the sum. And we have 1 power of GS here. Here you can see both of the GS's, but when you square this, you get the GS squared. So that's the one real emission diagram. And then there's a quark emission, or it could be anti-quark. I'm not going to draw that one separately. So we can have an incoming gluon collide with a quark and produce a Z and a quark. And we square that matrix element. And here the QCD coupling is over here. Okay, so those are sort of the generic contributions. Everyone comfortable with that? So yeah, so both contributions diverge. So we're going to use dimensional regularization, D equals 4 minus 2 epsilon, to regulate them in the same way that you often used it, probably more for ultraviolet divergences in your quantum field theory course. I realized I forgot to do something I promised to do, which was just draw a sketch of the parton distributions. So we're going to come back to the divergences, but I just wanted to sort of give you a flavor. Yeah. Because it's too white now. Okay. Well, I'm almost out of time, too. Let's just use this one. Very good. Okay, so this vertical axis won't really matter too much to you, but what I'm plotting here is x times FA of x, and mu f is 100 GeV, which is a typical scale at which you want to evaluate these. And this is x, and this is x equals 1. And all the parton distributions have support only from 0 to 1, because they can't have more momentum than the proton has. And basically this is the bottom quark inside the proton, the charm. I should really draw these. Now I'm going to totally mess this up, but okay. I'm a theorist trying to draw something experimental, so. Really, the most important thing is probably just this, that the gluon distribution can only be plotted on the same plot if you first divide it by 10. In other words, there are a huge number of gluons inside the proton, especially when you go down to very small x. These curves here are not directly for u and u bar separately, but this is for the difference of u minus u bar and d minus d bar. This is called the valence part. So because there are sort of two up quarks in the proton and only one down quark, there's a bigger bump in the valence distribution. Oh, and I should have also said this is a log plot. So this is 0.1, 0.01, and 0.001. Anyway, for the Higgs at the LHC, you're down in this region. Those are the relevant x's. So the gluons are enormous, and that's why even though you have a loop process, that's the biggest cross-section for making the Higgs. And also, the C quarks are just as important as the valence quarks down here. Although when you get out above a tenth, then it makes a difference that you have more up quarks than anti-ups and so on. So now I'm pretty close. I'm at the end. So I think it's a good time to stop. And tomorrow I'll go through the structure of these infrared divergences and how they cancel. And then we'll just sketch out the N and LO and move on to other things. So that's all for today, unless there are questions. Yep.
So is the fact that the gluon PDF
well, it's more than that. It's also additional soft things on top of that, because all of these there are processes that all involve collinear divergences. So we will see that when I draw an X here, it means that this thing can almost be on shell, and so there's a collinear divergence for gluons to split to QQ bar. There are collinear divergences for quarks to split to quark glue, and there are collinear divergences for gluons to split to two gluons. The real difference has to do with the dependence on the momentum fraction where you split. So you can split, and the sum of the two momenta has to equal the original momenta. Let's call that 1. So there's a splitting fraction. We'll go over this more later. Z and 1 minus Z. And this formula, I think it's something like Z squared plus 1 minus Z squared. But these formulas have more complicated dependence on Z, and they have singularities when, let me draw it backwards, when Z goes to 1. Anyway, well, what that means is that, or Z goes 0, depending on which way you look at it. What it means is that the gluons like to be radiated soft, and so they tend to build up more at smaller x because of that. So they both have collinear divergences, but the gluons have soft divergence on top of that. But then the gluons, once they're down there, they also drive a rise in the quarks, but as a secondary thing, so the quarks are never quite as high as the gluons down there. Any other questions?